Hello, people. By the way, from yesterday's two classes, yesterday's class, these were the two questions. Anyone tried them or like anything? Like, if people did try and they want some hint or did solve it and want to discuss that sort of idea, I'll probably do. But if not, then we can just start with the other stuff. I did, got it, I think. Okay. So, Pranjal, which one? Okay, both of them. Okay, cool, both of you. Although Pranav, I'm pretty sure you've already done these questions with me, literally. Okay, okay, you did the second one. Okay, let's do the second one first, because that's I think slightly on the easier side also and quite nice. Um, so what do you think the answer is? Okay, correct. In fact, in general, if you have n babies, then the answer is like n by 4. Um, and how do we prove this? Okay, I guess people have the idea. It takes time to write on chat. So I'll probably like this. Yeah, yeah, exactly. Basically that. So basically you can imagine like n people in a circle and if a certain baby is unpoked, then that means that the baby to the left of it or whatever chose to poke this one. And on the right chose to pick this one. So since every baby we're assuming is randomly picking, so there's 50% chance that it picks this one and 50% here. So the probability that this happens is actually like 1 by 2 into 1 by 2, because both of these events must occur for this guy to be un. So basically, we can say that the probability that each baby is uncooked is 1 by 4. And so then we do the standard, indicator variable stuff. So we can make an indicator variable xi, which is 0 if the ith baby is poked and 1 if it's unpoked. And the expected value of xi is 1 by 4. And if you add all of them up, you get n by 4. And that's actually the number of babies. I guess that's basically what people would have done. Is that clear with people? Okay, cool. The other question is slightly trickier. In fact, like quite non-trivial. Um, yeah, the question basically says 100 shoelaces. You have like something like this. Forget 100, let's just do with 4. And at any point, there are right now 8 ends over here because 1, 2, 3, 4, 5, 6, 7, 8. And you can pick any two random ones of these. They could be from the same one, they could also be from different ones. If you pick from the same one, let's say this and this, now this just becomes a loop and you forget about it. And if it doesn't become a loop, if you choose to pick, let's say, this one and this one, now it becomes a single thing with two free ends. So basically, these two things vanish and they get tied together. And the question, there are two questions actually. Expected value of number of steps and expected value of number of loops. So this one is kind of troll, number of steps, because the idea is that each time the number of shoelaces reduces by 1. So it just takes that many steps, like 100 steps or whatever. Um, but the more interesting question is the number of loops. And Pranjal seems to be getting some idea. For the first one, we do the first step and get 99 shoelaces, and go down, you get 100. Is this for number of loops? Okay, that was the first one, yeah. Um, so yeah, now the question is, how do we do the second one? That's the main crux of the question. So basically, as I said, like there are only two main possibilities. So you know what? Let's just consider both of them. One is that at the start you pick the same shoelace ke both ends. Now, probability of this happening is like, yeah, it's like Markov. Yes. So the probability of this happening is like 1 by n, because essentially you pick one random free end but then the other one gets forced. And the no, it's not 1 by n. Sorry. Ah, it's like 1 by 2 n minus 1, I think. Right? Uh, okay, I mean, if you want to do it more thoroughly, what you could say is like there are 2n choose 2 possibilities, and you're looking for one of n things. Yeah. So this comes out to be this, I think. Yeah, n by 2n minus 1 into n. So this cancels. And yeah, this is the probability that you ended up choosing the same thing. And now they're asking you expected number of loops. So the idea is basically that if this became a loop, now it's not really contributing, and it's equivalent to solving the case for like f of 99. Basically, if there were with 100 things, there were these many loops, then 99 kile, whatever the answer is, plus 1. So you get something like f of n minus 1 plus 1. This is f of n. And in the remaining possibilities, which is, oops, which uh, is yeah, which is like plus 2n minus 2 by 2n minus 1. Now what has happened is basically you've tied ends of different things. So actually this doesn't really matter. It's essentially like you only have 99 shoelaces now. You can imagine this was like the same shoelace you started off with. It like doesn't really matter. Uh, so because essentially like it's just a longer shoelace, but you don't care about the length. So you can imagine it's of length 1. So you can actually say that in these cases, it's just equal to the previous value. And if you solve this, you'll get Fn equal Fn minus 1 plus 1 by 2n minus 1. And for F1, you can get answer as 1. So you get 1 plus 1 by 3 plus 1 by 5 plus 1 by 199. Okay, cool, Francis, you're the same. Okay. So these were the two problems from yesterday. Not really going to be relevant to what we're doing today beyond the point. Of course, expected value is kind of the crux, but like you don't need to be knowing all these equations and everything. Um, like the idea of solving equations, etc. So today what we're going to be doing is this amazing technique called the probabilistic. I hope I keep spelling it right. Method. And essentially what this says is, if you can show that the expected value of a random variable is, let's say, 5.3, then if you look at the sort of range of this random variable, like it's basically a function, right, which is giving you certain values, and you have taken like the average, like the weighted average of them, and that you've got out as 5.3. So the idea is that there must be something that is below 5.3 and something that is above 5.3. Like something like 5 or something here, 5 or 4 or whatever, and something like 6 or 7. And the idea is because we're always usually our random variable only takes integer values. If you get a fraction, that's kind of nice because that tells you that floor of EX always exists and floor of something that is at most rather, because basically you can guarantee something in like 1, 2, 3, 4, 5, or even negatives, whatever, depends on what the question is. The idea is basically that, if your average is 5.3, you can't always be above 5.3. At some point you'll be at most 5.3, which time you'll also be at most 5 because everything was an integer. So that's going to be our main idea throughout this class. And it'll be a lot more clear when we do a couple of problems. So I'll just select a problem from here. Yep. Yeah, I think this is a quite nice question to motivate the idea of stuff. It's too big. It's fine. Okay. Yeah, this is the problem. You people might have seen this. You might have seen this in the context of double counting, or maybe even probabilistic. I don't know. But this problem has a surprisingly neat solution using uh, expected value and probabilistic. So let's think about it for a minute or two. Or maybe I can just give this one out directly because it's the first one, and then people can think from whatever people prefer. People prefer to try it for a second, for a minute or something. Okay, people are saying we prefer whatever you prefer. So I'll just this one I'll give up, but after that, next time onwards, people can think. Um, so basically, the idea here is like, okay, what's the question first of all? There are 200 students, and they had six problems. It's like the IMO. Each problem was correctly solved by at least 120 people. Prove that there must be two participants such that every problem was solved by at least one of the two. So basically, they're saying out of your 200 people, you can choose two of them, A and B, such that if you take the problem solved by A, let's say A solved like, I don't know, 1, 2, 3, 6, and B solved, I don't know, 2, 4, 5, 6, something like this, and you take their union, then you'll get everything. So like all problems. So basically every problem should have been solved by at least one of them. So one is solved by this guy, two also, three also, four, five, six. So at least one of them has solved each of the questions. So that's nice. Um, yeah, so I was trying to give A007. Um, yeah, so anyway, yeah, the basic idea here is going to be we don't know who A and B are. So why not choose randomly? Um, so yeah, the point is basically that you pick two random people and calculate how many questions they would have solved at an average. So the expected value of the number of solves in their union, in some sense. And the hope is that the answer we get is something like, or okay, maybe a better way to think about it is, I'm not sure whether I should. Okay, fine. Yeah, this is fine. So let's say we took A and B randomly. Now we want uh, so each problem we consider, the thing is that this is the important information. 120 students out of 200 have solved it. So if we pick A randomly, there's a probability that is at least 120 by 200 that he has solved the question, because we picked him randomly out of these 200 and 120 have solved it. And that is actually just 3 by 5. So the probability that he didn't solve it is 2 by 5. Similarly, the probability that, wait, maybe I should write stuff down. So probability that A didn't solve P1 is 2 by 5. And probability that B didn't solve is also 2 by 5. So probability that both didn't solve is like the product, because you need both things to hold, and they're independent events because A and B are chosen independently and randomly. So 4 by 25 is the chance that both didn't. So I mean, we can do 1 minus 4 by 25 and say that this is the probability that at least one of them has solved the question. So we get 21 by 25. This is the expected value of the random variable xi, where xi is 0 if both didn't solve and 1 if one others. Okay, so basically the idea is that the expected value of number of questions solved will be 6 times this, because there are 6 problems. Uh, So you can say that the expected value of the number of solves is this. And if you do this, this becomes 126 by 25, and that's like ridiculously close, because what you get is 5 plus 1 by 25. And this is actually like 5.04, right? And now the idea is that if whatever A and B we chose, the value of the union was at most 5, then the average would also have been at most 5. But the average is 5.04. So at some point, this thing must have been at least 5.04. And at that point, it would have been at least 6. So there are some two people who solved all this. Also, just a note, there's a slightly different way of doing this. What you could do is, count the inverse. So check how many problems A and B both didn't solve. So there you would get 4 by 25 into 6. That will be 24 by 25. And this is less than 1. So you can say at an average, A and B uh, don't solve less than one problem. So at some point, like both of them wouldn't have solved less than one problem. So both of them together would have solved all 6 problems. Like it's the same thing. I've just done 1 minus 6 everywhere. But I think this is the more well-known solution. Like, but whatever, they're both equivalent. Sometimes this will be a lot neater. Sometimes this will be a lot neater. Sometimes both will be equivalent. So we'll see as to what we want to do in general. Is this clear to people? Should I explain how we got greater equal 6 using this 5.04 or anything of that sort? Okay, clear. Cool, cool. Uh, yep. So let's do a couple more questions. Now, this one was like a kind of decent question, and the sad part is it can be solved quite easily even without probabilistic. Let us do one question which really shows how probabilistic can murder innocent problems. So this is the question. The n real numbers looks like algebra, but apparently not. Not all zero. Some is zero though. So we have sigma ai is zero. Prove that we can label them A1 to AN in some order so that this product is less than 0. Oh my God. How are you ever going to do this with probabilistic vector? Um, okay. Yes, 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 you're getting there. We'll just wait a bit so that others can also think about it. That's it, by the way. Yeah, this problem is actually tricky to start off with. And uh, oh, yeah, not all zero though they've given you, right? If, yeah, I think that equality only comes when everything is zero. Okay, okay. Um, cool. No, but then at the end, you will also have less equal if you're using equal to zero. Yeah, okay. I don't know. Okay. Anyways, so the idea here is that we're going to absolutely destroy this question by saying that the expected value of this thing is negative. So if we can show expected value of A1, A2 is negative, and this all of these are symmetric, so their expected values are all negative, then the expected value of this entire thing by linearity of expectation becomes equal to their sum, so sum of lot of negative values, which is also negative. And so we can get something that is negative because something will be at least the average or at most whatever. So yeah, the question really becomes how do we show that taking any two random numbers out of our set of n, the expected value of that product is negative. And this is mostly just algebra, nothing too fancy about this. Basically, what you do is sigma ai is zero, sigma ai square is zero, which is actually really nice because it basically means sum of squares, a2 square, blah, 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 an square, plus 2 sigma ai aj. This is just the expansion of this. is equal to 0. This thing is positive, so this thing has to be negative. And so if the entire sum of the whole thing is negative, then if I pick two things at random, logically also, the expected value should be just because all of these are kind of in some sense symmetric, you can just divide by and choose two or whatever. Um, so yeah, the idea is if the entire sum is negative, but the expected value of a random thing was positive, then we could have added all of those things and said expected value of the entire thing should be positive, but then we know that it's negative, so contradiction. Basically, the idea is you get A1, A2's expected value is um, less than 0. And so you can say similarly, E of A2, A3 is less than 0, and so on. Uh, and E of A and A1. And this is the really cool step because this and this are not at all independent of each other. Because once you have fixed A1 and A2, this thing is fixed. So you only really get to vary A3. And so its expected value need not, like, in that sense, be negative anymore. But because we have linearity of expectation, which says that even if stuff is not independent, you can just add it up freely. You can just say E of sum AI plus 1 is also less than 0. Hence proved. Because you're just adding all of these inequalities. And like that is seriously cool. Because when I saw this question, I saw almost immediately that you could do this. It was like, why? Why did this work? Like this is not supposed to work. Something like this just shouldn't work because this is not even like something that's symmetric. Like it's only cyclic in its nature. So it's not even like you're considering all possible things. You're only taking some subset of them, and it's still working out in your favor. So like I was like, okay. I mean, I know that works, but I feel kind of depressed by that because it's just it's like you killed the problem, destroyed it, murdered it. And that's really what probabilistic method allows you to do sometimes. Like, this looks like a fairly hard question because, I mean, you have to label the numbers in some order. So, without doing this with probability, like picking stuff randomly, if you actually had to tell what order to pick them in, I have no idea how would you solve this question. I guess the closest thing you could do is something like try to alternate signs every now and then. But then the issue is you could have everything positive and one thing which is very negative. So you can't really alternate signs. So I'm not really sure what you would do actually. But apparently you can just use this very cool fact and you'll be done in 30 seconds. So yeah, this is kind of the power of expected value and probabilistic. Um, this is clear to people. Are people convinced that this works? I hope not, because it does take time to get convinced. Okay. Oh, you got convinced. That's sad. Yeah, it's okay. I'll give you another question for you to not get convinced with. We'll do another question which gets absolutely brutally murdered. And if you get convinced again, that's just unfortunate. Okay. Yeah, this is another question. In a class, each boy knows at least one girl so that we can choose a group of more than half the students so that each boy in the group knows an odd number of girls in the group. Um, yeah, so basically you can imagine boys and girls as like vertices. It's okay if you don't know graph theory. You don't use anything fancy in this question. Um, Basically you're thinking of red points as boys, black points as girls, and each boy knows at least one girl, so there's like we join them with an edge if they know each other, like that's just basic ideology here. Something like this, I don't know. Yeah. uh Wait, is this just done trivially? I'll make it harder. Yeah, you have something like this. So here if you see, A knows two girls, B also knows two girls, C knows three girls, and D knows two girls. Oops, chat messages. Bipartite graph. What was the definition of that again? Definition of what? Bipartite? If no odd cycles. So you can't have a triangle or something. Because if you had a triangle, then it would sort of mean there's an edge within the same component, which is not allowed. Basically, you should have two different components so that, boys don't know other boys, or at least we don't care about that. And girls don't know other girls, or we don't care about that, at least for the question. All we care about is boys knowing girls or boys not knowing girls. Yeah, that's the basic idea. And yeah, so the question asks you to basically, this thing is called the degree of the vertex. Again, it doesn't really matter if you don't know this. It's basically saying boy knows two girls, so degree of boy is two. Similarly, all of these exist. And you want to, from your graph or class, you want to delete some of the people. So, for example, I could choose to delete this guy, this girl, uh, or maybe, okay, I delete this guy and I delete this girl. And now, if you notice, this boy knows one girl because this girl is gone. This boy is gone, so we don't care. This boy still knows three girls, and this boy also knows one. So now all boys know an odd number of girls, and we're happy. And like the issue is like we can always do this by deleting almost everyone because like I could like delete almost everyone so that there's only one boy, one girl who know each other, hence proved. But the cool trick is that you can do this while deleting few people. So you're deleting at most half the people. One can choose a group of more than half the people, so you're deleting at most half. But this condition is holding that each boy knows the half odd number of girls. Here, in fact, we got something much stronger. Like there are nine people and we only had to delete two. But in general, this states that you can delete at most four and it'll work out. Okay. Yeah, randomly choose a group first. Okay, that's interesting. Um, there's a slight issue when you try to do that because let's say you try to say I select each person in the entire class with probability half. Now the issue can happen if a boy exists and an odd number of and an even number of girls he knows exist. And yeah, how exactly are we going to deal with stuff? It's kind of slightly tricky because the other case could also have been that the boy himself is gone, in which we don't care. So, first of all, what exactly are we trying to count? Um, yeah, this is not so easy because like what of the expected value of something we need to find, but of what? Um, like we know expected value of the entire group is n by two, but then a random selection does not necessarily satisfy our demand. So we're not exactly happy. Like what we would want is that we take a random selection satisfying our demand, and then the expected value comes out as effective. So it's not useful to first set off your expected value and then try to fix stuff. It's better to first fix stuff and then find the expected value. So maybe instead of picking everyone randomly, let's only first pick girls randomly. And then if some boy ke liye life is not working out, like he knows an even number of girls, then we just delete that boy. And we figure out at the end how many boys we would have needed to delete and how many girls we ended up deleting. So basically the thing is you delete each girl with probability half. So the expected value of number of girls, uh, number of girls in this new graph is like original number of girls by two. Um, and the question now is how many of the boys are left? Because if we can show that around half the boys are left as well, then we'll be done. because then we'll have b by 2 plus g by 2 by linearity of expectation again. Um, and that's again quite non-trivial as to how linearity just works. Um, but yeah, we need to show that basically take a random boy, the probability that he has an even number of friends is half. Why is that true? Yeah, or even equal probability. That's the sort of thing you basically want to prove. Okay, maybe this is not the best way to prove it. Basically, the idea is like, let's say, okay, the boy had like n friends, uh, and you only consider the first n minus one of them and take the last one finally. So you see, in n minus one, may say how many girls are there. If this was odd, then we would need this girl to not exist anymore. So that happens with probability half. And if this was even, we would need this girl to exist. And that also happens with probability half. So either way, like there's a 50% chance that the relation with this girl kind of works out so that the total thing becomes odd. So the idea is that the probability that this boy exists in our final graph is also 50%. So we can say that E of P dash is also half of P. And now by linearity of expectation, we can add the two things up because E of B dash plus G dash is the size of the class. And this will become B by 2 plus G by 2. And that's half the size of the class. And so basically you're saying that the expected value of the size of the class is half the class. So at some point it'll be more than half the class. And like it makes sense here. I'm not saying that this is completely unbelievable, but it's really like non-trivial and quite interesting that you got that this is half, but the fact that you can just add them up together and say that at some point both of them were kind of better. Like it's like you can it makes sense to say that at some point you would have had more than half the boys, at some point you would have had more than half of the girls. But the fact that you can say at some point you would have had more than half of the class by linearity of expectation, that's really interesting and cool. Um, yeah, that's the basic idea of this question. Any doubts in this question? Because this is really cool. The fact that you can add them with linearity. And this is why it's so important to have like a firm grasp of something like linearity of expectation. Um, oh, because we just picked each girl with probability half. Like 50% chance that we pick a girl. So like we can again define E of xi as the indicator variable that represents the that is 0 if the girl doesn't exist and 1 if it exists. The value of it is half. You add all of the stuff, you get G by 2. Cool. And if you're writing it in an exam, this is a very good way to write it. So do this. Don't just directly say G by 2, although they will probably not care. But this is a cool way. And also, it's like kind of formalizes your ideology of thinking, at least for me, because when I would originally say something like B by 2 or N times P, in general, I knew it's correct, but I didn't like. I knew that it's a sum of n small things, but I didn't really know how exactly I should define each of those small things. And when I, read about indicator variables, that sort of made my life very nice because it basically formalized my way of thinking about stuff. Um, but yeah, that was the basic idea of the question. Okay, we have we have a slightly algebra heavy question. Not really algebra heavy, but again, this is also a very cool question. Yeah, and like the motto of this class is like, you don't know what to do, just do stuff randomly, hope for the best, take above the average. Are you done? Oh, thank God you're done. If you weren't done, then back to square one, try something else. Also, this question is slightly tricky to understand because residues and all. So basically, what this is saying that you have 1, 2, 3, all the way till n square, and A is basically a subset of this. Uh, let's say this, and mod of A is n. So it's an n element subset, and this is given to you. And now what you have to do is find a B also subset of S, so that mod of B is also n. And now, let's say A was something like, I don't know, 1, 3, 7, and B is something like 2, 5, 6 for n equal 9, n equal 3, so n square equal 9. So now you basically add up each pair and take that subset, and also take it mod n square. So you'll get like 3, 5, 9, we can make 0, or we can keep it at square, whatever. 3, 5, 9, then 6, uh, whatever, 8, 12 becomes 3, 3 is already there. Um, and then whatever, I'm saying whatever too much. I might have missed stuff, but you get the idea. You have to add each pair, take all of the residues, and see what all comes up. And you want to construct a B so that this set contains at least half of those residues. Residue basically means one of these things here. Uh, yes, that is going to be what we do. That's like our entire life goal is that only. Choose B randomly, hope that the thing is at least n square by 2. But yeah, the difficulty of the question is proving that it in fact is n square by 2. And actually, if you come to solve the question, you will realize that n square by 2 was ridiculously weak. In fact, you can say 1 minus 1 by e times n square. And this is like 1 minus 1 by 2.718. That will be like around 0.66. Not ridiculously weak, but somewhat weak. Like this was just zero point 0.5, but you can improve it to this sort of 0.66 or something. In fact, more than that, right? Or less than that. Less than that. So like maybe 0.6 or something. Okay, but either way, this looks scary. I agree. 1 minus 1 by e. From where did e come? But it comes somehow. We'll not worry about it just yet. In fact, we'll just prove for by 2 for now, and then we'll see later on by how we could have improved it. Yeah, as Pranjal said, we pick P randomly, hope for the best. So the idea is you take an element subset. So each element, the probability that it exists in B is 1 by n, like n by n squared. That's 1 by n, right? And now you work backwards, right? Because A plus B, let's say, does not contain X does not belong to A plus B. A plus B represents this thing. So yeah, if X does not belong to A plus B, that means that if let's say A was like A1, A2, all the way to A, and that means that X minus A1 is not a part of B. Because if X minus A1 was a part of B and A1 is a part of A, then you can add up the two of them and you get X. Similarly, you can see that X minus A2, X minus A3, all of these should not be a part of B, right? So we need to figure out the probability of none of these belonging. And logically, that seems unlikely, right? There are n numbers. The fact that none of them exist, that's kind of unlikely, but maybe possible. Yes. Um, so this thing, the probability that it exists is 1 by n, we saw. So probability that it doesn't exist is n minus 1 by n. Similarly, all of these also probability that they don't exist, probability is n minus 1 by n. But the fact that none of them exist, you'll start having to multiply everything. And because there are n such things, you'll have to do this. So this is basically the probability that x is not in a plus b. So we can say probability that x is in a plus b will be 1 minus. Also, I'll write this as 1 minus 1 by. Let's do it. Okay. This is the probability that x belongs to a plus b. And so we can now do our random indicator variable stuff. Basically, we can say that the expected value of the size of a plus b is the sum of this probability n square times. Because if each person comes with this probability, the total size is going to be n square times this. Again, you can say xi is 0 if x doesn't exist, does not exist, 1 if x exists, and you'll get e of xi as this probability. And so the total thing will be n square times this because there are n square possible residues. And you want to show that that's at least n square by 2, right? That expected value is at least n square by 2. So it's sufficient to show that by like canceling the n square that would have come out on this thing. Basically, you want to show this is at least half. So this is our objective. This is the where the algebra kicks in. Yeah, you can see E now because this thing, the limit as n tends to infinity is E. But yeah, we don't need to use limit, but it's always less than 1 by E. That's what we basically do. But yeah, for starters, we can rearrange. So we get half at most 1 minus 1 by n raised to n. This is what we need to prove. So anybody with any ideas on how we can do this? It's not easy by any standards. There is one slightly smart way actually. What you could do is you can say this is equal to n minus 1 by n raised to n. And because I don't really like half, I kind of like 2 better. And I, in general, like addition better. Like I somehow want plus here. Uh, because then I can use this Bernoulli's theorem. Basically, Bernoulli's theorem would say 1 plus 1 by n, the whole raised to n, is more than 2. Because if you do binomial expansion, then you get 1 plus n into 1 by n plus n choose 2 into 1 by n squared, etc. But these first two terms sum itself is 2, and then you have positive stuff. So this is at least 2. And that's what we'll basically prove. Because if you take reciprocal on both sides, it basically becomes this, somewhat similar to this. So what you get is 2 has to become less equal, sign switches. And you get 1 plus 1 by n minus 1 raised to n. So it's not n raised to n, it's n minus 1, but basically equivalent because same Bernoulli idea applies. Now instead you'll have 1 by n minus 1 here. So you can say that the RHS is, you can say it's at least 1 plus n by n minus 1, which is at least 2 because this is more than 1. Yeah. Yeah, this is one way to prove it. Other stuff, okay, in general, also this just holds that 1 minus 1 by n raised to n is, wait, I have to think of its sign. At most 1 by e. Yeah. And because 1 by 2 is, right? Yeah, yeah. I have to think twice before doing fractions. Yeah, and this can also be proven. This is not too hard actually, because the limit as n tends to infinity is actually equal to this value, and you can show that this sequence is like decreasing or whatever, increasing constantly, and so it's always below 1 by e. Yeah, exactly. Like it's so hard to think whether 1 by e is bigger or half. I have to first, cross multiply and think. Yeah, I don't get how people do stuff immediately with fractions. Anyway, stuff works out. But yeah, the cool part of this proof is really getting all of these things. And this is something that comes up a lot in probabilistic. Not too much in the questions I will do today because they're not really this themed, but I've seen this come up a fair bit. And E comes up a lot in probabilistic because you always get exponentials when dealing with probability. And so it is kind of useful to know stuff about E and log and stuff like that. Um, but it's not necessary by any means. Plus, like, it's okay if you don't completely get it right now. Maybe after a year, when you've studied stuff more thoroughly about, real analysis and those kind of things, then it'll be a lot more natural to you. But as long as you have a basic idea of how stuff works, it's good enough. Okay, that was a cool question. Any doubts on that, by the way? People can keep asking. I will find the next question. Oh, this class ends at 8, right? Okay, still like 37 minutes. That's good. Can probably do that. Do people want like easier questions or harder questions? Because I have like some easy questions and some hard questions left. Harder. Okay, we have one vote for harder. If people think that this is shader, someone wants shader also. Okay. Medium. Okay. Um, Yeah, we'll probably go with medium. That's fair. Still. Or okay, how comfortable are people with graph theory? Like I will explain everything required for the thing if I'm using graph theory, so don't worry. But just asking, moderate, like basic idea आ जाता है कि what is vertex, what is x, ठीक है ना? But I'll make sure that there is no issue of that sense. Yeah, definitions. Okay. Yeah, I don't think you will. If you know this definition, then pretty good. But if you don't, then we will define stuff. Yeah, this is the question. Show that R k comma k is greater equal to raised to k by 2. People know what is R? Yeah. You don't need to know Thurin's theorem or not. Thurin's theorem probably has a probabilistic proof. I'm not sure. Yeah, exactly. Ramsey number. Yes, I will explain. I will explain. This is the Ramsey number, basically. Um, Essentially, you might have seen this question before. There are six people, and each pair of them are either friends or enemies. Friends or enemies. And show that there is a monochromatic triangle. So there's a three people who are either all three of them are friends or all three of them are enemies. That is I think a fairly well-known question. Yeah, I will define Ramsey and all. Don't worry. Um, yes. So have people seen this, by the way? Like you have six people, and each pair of them is either friends or enemies. You want a triangle of either all three friends or all three enemies. Okay, you've seen it? PHP. Yes. This is a PHP argument because um, you can say that he has five friends. So either three of them are all friends or three of them are all enemies because either three and two or whatever. So let's say three are friends. And now these pairs can't be any like if this is a friend, that's bad. So this is an enemy. So this is also an enemy. This is also an enemy. So you have an enemy of triangle of enemies. Hence proved. But that's not really relevant too much. Basically, this is kind of a generalization of this question. Now, what you do is you have um, R k comma k numbers. Don't worry with the notation. We'll just let's say n is R comma k. And so you have n people, and each pair of them is either friends or enemies. And you want to find k people so that each pair within those k were all friends or each pair within those were all enemies. Is it an old IMO problem? I think it's way too famous for that. Might be a Russia Olympiad problem or something. 1972. Okay, you may be right. We can check later, but yeah, you might be right. But I would be actually very surprised if this came on IMO. Like I thought this is like some research papers have been on this since like 1800s and all. So surprising if this came on IMO. But yeah, the funny anecdote about Ramsey numbers is okay, sorry, the question was K people and either each pair within them should be friends or each pair within them should be enemies. So something like you have 100 people and you should be able to select four of them so that all of them are friends or all of them are enemies. And you pick n to be the smallest such number. So obviously, if your n is very small, like n equals 3 or 4, then I can construct a counter example where, people are friends or enemies, but there is no such thing. In fact, I can make like rk comma k less than k. And then obviously there'll be no set of k people so that all of them are friends, obviously, because there are no k people. In fact, the question here to prove is that rk comma k is at least exponential. So you can prove that if you want stuff to work out, then it'll be very, very, very big.
Why
Uh,
two Ks?
what?
Why is it K comma K?
Oh, yeah. So in general, it's R A comma B, and that means either A friends or B enemies. Like A people who are all friends or B people who are all enemies. And why this is defined like this is because you can define a recurrence relation that is saying something like this, R A comma B minus something. That's not really what we're looking to do here. In fact, this can be proven with elementary stuff, with like pigeonhole. And the proof is similar to what we did here. No, not here. Whatever. In the three people, two people thing, the six people card. The proof is very similar to that. And that's why it's useful to define it even when friends and enemies ke things are not necessarily equal. We're minimizing R relative to K. Exactly. Yes. And we're showing that that minimum is already very big. It's not even this. It's like even bigger than this. But we can show that it's at least this big. Yeah, Kanav took a class on extremal graphs.
Ramsey numbers also you took.
Like he might have done it within
No,
extremal graph, right?
aligned
Huh?
only. It was a different class.
Okay. Okay, whatever. Yeah, possible. But yeah, this is the reason why you say k comma k and not just rk. Although, like for our purposes, we don't care. Yeah. So the question is, given a very big set of people, you want to show um, that you can make some arrangement of friends and enemies so that this k people thing never happens. And basically, that would mean that that large n fails. And yeah, so yeah, okay, maybe I should have been more clear. The question rk comma k being more than 2 raised to k by 2 basically means that if I take a set of, let's say, 2 raised to k by 2, even this, but let's say minus 1 people, there is some arrangement of friends and enemies that I can do. Like I can define this guy to be friend of this guy to be enemy of this guy, etc. So that this never happens. That there are no K people ever, so that all of them are friends or all of them are enemies. And this looks really fancy, but the proof is quite like normal probabilistic stuff. The construction. Wait, what construction did I reveal? Oh, huh? No, I see. The entire point of probabilistic is we don't find constructions. We do stuff randomly and say, hopefully the construction exists because at an average it's quite low, so construction has to exist. Like that's the entire point of. So there is two type of things in life. There is deterministic and there is probabilistic. The other day I had an argument with Pranav because Pranav gave me this question which I won't reveal because of certain things. that basically he said that, this is optimal because I can't think of anything better. I was like, there can be like probabilistic random stuff that ends up somehow magically doing better. You can't um, disprove me. So until and unless you prove that value is optimal, I'm not going to accept it.
I mean, there
But
is
yeah,
a proof.
and
It's just I don't remember the proof. I told
yeah,
you, right?
so find the proof. Okay. But yeah, the basic idea is that even if you go into computer science, there is, a lot of this about doing stuff deterministically versus probabilistically. I think they don't usually say probabilistic. They call it more like non-deterministic, but that's basically the same thing. Uh, and yeah, there are a lot of computer programs which basically try to do stuff randomly and they don't work out immediately, but if you keep trying, it'll eventually work out. And because you are doing them completely randomly or pseudo randomly, sort of, it's guaranteed to work out fairly fast. That's the ideas on which stuff like hash maps and all exist. Um, Whatever. I'm not getting too much into that because honestly, I don't know too much, but at least that's what I've been told. These kind of things happen. Yeah. So this is what we need to prove. In fact, we'll prove even this. So we don't need to care about greater equal. We'll just prove greater than. Like the bound we'll create will not even be closed. So it does not matter. And also maybe we'll have to say large enough key or something. I'm not sure. No, we don't need to say large enough. Okay. What is R1 comma 1?
Okay,
Okay, don't think about R1 comma 1. Yeah. Oh wait, it'll hold even then because this just says 2 raised to half. That's 1 point. Whatever. Yeah, go ahead, Pranav.
yeah. So, uh, pick a K-line cycle, and the probability that it works is
1 second. I should clarify. K people means click on K people. So each pair of them should be friends. Even it's not saying 4 people, it's saying even these diagonals. Sort of.
right. I forgot
So
about that.
not cycle.
Yeah.
Yeah,
Pick a
so
K,
okay, pick a K click. Okay.
and probability that it works is 1/2 to the power K
No,
plus
1
2,
second.
right?
What have you done? What have you done?
And I'm just saying that probability that that K clique has are all friends or enemies.
Start from the beginning. What have you done? You've done stuff randomly? Like, have you decided? So the basic way to start would be, say, I decide whether 2 people are friends or enemies randomly. So there's a 50% chance A and B are friends, 50% chance A and B are enemies. Right? That's what you've done.
Yeah.
And now you take a K clique, okay. And the probability that each pair of them are friends or each pair of them are enemies. That's what we need to find.
Yeah.
And that is,
1/2 to the power K plus 2.
are you sure?
Yeah.
No, it's 2 times this because they could all be friends or they could all be enemies.
Okay. Just
uh,
for that.
but yeah, that's the idea. Basically, you do stuff randomly, and now take a random key. And the probability that stuff is not in your favor is this. Now what? Also, people can still see my share screen, right?
We can only see your whiteboard.
Yeah, like the whiteboard. Oh, sorry, I've not been checking last 5 chats. Are you presenting or are we solving? We're solving, like we're just discussing. Um, We just choose a k set of vertices, right? Not a clique. Yeah, we just choose, yeah, like everything is a clique basically because all edges are connected. It's just some of them are red, some of them are blue. Red means friends, blue is friends. Yeah, you're right. K people we choose. Okay, you repeat this for KCN. You mean NCK. Why do you people write it KCN? What is KCN?
Yeah, I thought it
Um,
was a compound for a second.
okay. It was a compound. Um,
It is, right?
potassium cyanide.
Yeah, fine. I was not wrong.
Okay. Interesting. Let's say we multiply this by n choose k. What does this even represent for starters?
This shows basically the expected number of K cliques which are good.
Really?
Yeah, like
Like
expected
what is this?
uh this is the probability that a clique works.
Probability that clique works. What do you mean works?
Like the clique is a good clique. Just define
But
good.
do we want it to be good or bad?
We want it to be good, right? We want it to be bad.
Yeah, exactly. We want there to be no clique,
Yeah,
right?
yeah.
Cool. We want there to be no clique. So this is not good. We don't want this.
No, no. What if you show that expected number of good cliques is less
Yeah,
than one?
exactly. That's what we'll show. Um, so yeah, we want to show that this is less than one. Basically, this is probability that the clique is good, and this is the number of cliques. Okay, I should call them k element subsets, as Pranav corrected me. Um, and this is basically expected value of number of good stuff. And if I can show that this is at most one, what does that really mean?
That there exists some construction for which this is zero.
Exactly. So if expected value of good is at most, okay, sorry, good means it's, by the way, a very bad thing to say. Pranav is just saying good. I don't know why. It should be bad. But good here means that all of the K choose two people are all friends or all enemies. Yeah. Good means
Yeah.
bad. Exactly. That's
Thank
how
you so much.
life works.
Rushil.
I agree. It's good in general, but for us it's bad because we want it to not happen. But
Sure.
yeah, and also note that this is one of those times where you really prefer to work with like the 1 minus x kind of thing. Like you prefer to work with these things. If you start trying to work with bad stuff, now the expression is horrible because you'll have to do inclusion exclusion first of all. So it's better to do the negative argument, whatever, 1 minus x thing. And that works out really well here because basically, if you can show that the expected value of number of cliques is cliques now here means that everyone in that clique is friend or everyone in that is enemy. Yeah, complementary counting. Um, if the expected value of that is at most one, then at some point in some random labeling, it would have been zero. And that random labeling, if we pick that for n people, that would mean that the r, k thing is false. We are done. Exactly. So all we need is this thing to hold, which looks kind of scary, but it's not that bad. We'll take this side. So we'll get n choose k less than 2 raised to k choose 2 minus 1. Yeah. And honestly, stuff like minus 1, we don't care about. But like as I told you earlier, like the bounds are going to be absolutely stupid. Um, First thing I'll do is I'll write this off in n into n minus 1 to n minus 2, blah, 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 n minus k plus 1 by k factorial. This is fine. And we know this is, I'm going to do stupid stuff, so I'll just do this. I don't care about all of this. We can get rid of it. Basically, this is just larger. And if we show that this is the 2 raised to thing, we're happy, right? And we know what do we want to show. We are okay. We have assumed for the sake of contradiction that n is at most 2 raised to k by 2. So we have assumed n is at most 2 raised to k by 2, or in fact equal to 2 raised to k by 2, and we're disproving this case, right? Um, so we can replace this by 2 raised to k square by 2 will become by k factorial. And we want to show this is 2 raised to k square by 2 minus k by 2. I don't care. Okay, I have to care about it, don't I? Because it's on the RHS side. This is about what we need to prove. And this is kind of trivial because you take stuff to the right side, you get 2 raised to k by 2, k factorial. And k factorial, if you just write out, it's like 1 into 2 into 3 into 4 into k. These are like k things, all are bigger than 2, and these are only k by 2 things. So it's like this is just far, far bigger. Because, okay, I mean, this is k minus 1 things, and this is k by 2 things. And each thing on this side is as big. So RHS is clearly much bigger as we wanted. Yeah. So, yeah, I don't know why the hell anyone would ask you to prove greater equal when bounds are like nowhere close to equality. Yeah. Yeah, that's
Plus one things.
what? Sorry.
To be exact, there are k by 2 plus one things. So the issue comes in k equals to 2 case, which is why
Yeah, I
don't.
don't care. I don't care about small numbers. Also, k equal to also, I don't think it would matter, right? Like,
K equal
like two people, one friend, one enemy. Ah, okay, fair enough. Acceptable, greater equal, accepted. Yeah. Whatever. I'll say k greater than 2. Be happy. Um,
does k equal to 3 work?
no, this is not even an integer. 2 raised to 3 by 2.
Okay, fine. Yeah.
Okay, yeah, I don't care about algebra. This sort of sad part of probabilistic. It's all so beautiful, like everything is brilliant, except at the end you still have to go and do that trash algebra. Yeah,
As-
but like,
Like
hmm?
scheme over. Yeah.
What?
Someone asked you to review the problem again.
Oh
Maybe.
yes, I will. Yeah, we will start from the start. Um, what is happening? It's getting hanged. Okay. In fact, I'll just, write stuff from scratch. I won't write in detail, but basically you're saying that, let's say for the sake of contradiction, rk comma k is at most 2 raised to n by 2, k by 2. So basically what we are saying here is we'll define this as n, and you define, so there are n people, right? And you want to come up with some sort of construction so that I say, these two are friends, these two are not friends, these two are enemies. I mean, not friends, enemies are the same. Don't get confused with that. Whatever. I came up with some weird construction so that given any set of k people, you will never have all k of them, all k choose two pairs being friends, or all k choose two pairs being enemies. Like there'll be something in your thing that's stopping you from saying that. Like here, these two people are enemies. Or if I took these four, then whatever. You'll never get a four clique. And clique here basically means everything connected. And you'll never have a four sized independent set, which means four people and nothing is connected, meaning all four of them are mutually enemies, like every pair of them. So instead of actually constructing this, we'll say, let's pick friends, enemies randomly. We don't care. There are n choose two people here. Each pair you just pick randomly. Hope for the best. 50% chance. And now we see any k clique. And what's the probability? Not k clique, sorry. People, set of k people. And we find the probability that it's one of these two. And the idea is that it only becomes this one if each of these worked out half, 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 half. So 6 times it would have had to work out. That's actually 4 choose 2. So in general, k choose 2 times, you would have stuff to work your way with 50% chance. Or this way, which is also equivalent. So you get 2 times that. So this is the probability that k people becomes k clique, or k people becomes what you don't want, right? Not like. So basically, if I multiply this entire thing by n choose k, which is the possible uh, choices for k people, this becomes like you can also have said this is the expected value of the random variable, where the random variable is 0 if the k people are liked and 1 if the k people are not liked, because everyone is friends or everyone is enemies, something like that. And so you can say that if this thing, this entire expression is at most 1, then we're happy because at some point it'll be 0. And when it's 0, that means that everything is liked for us, which means that there is no k clique and no k independent set. So n cannot be that small. N has to be bigger. And now it's just algebra. Now we do stuff. Okay, time to recheck. Yeah, this is slightly sus to me. What if the chance is higher and lower and not random? Can we assume half just like that in such a varying term? Okay, yes. So you cannot assume half if they gave you what to do, but you decide what to do. You said assume each pair is friends with 50%. Basically, you want to make a construction. You want to construct a set which works out. Because you don't know how to construct it, you are doing stuff with 50% probability, um, and hoping for the best. So it's not like you are you are given a graph and you're trying to figure out something. You are creating all sorts of graphs. This is implying equal friends and enemies, right? It's implying equal number of expected value of friends is equal to expected value of enemies. But number of friends and enemies may not, because there is always, like, if you choose everything with 50% chance, there's a chance that everyone became friends. Obviously, that chance is very low, but it exists. Um, but the entire point of the question is that we don't care about every possibility. We are just hoping that there is some good possibility. You're proving the worst case with worst probability is still fine. I won't say worst probability because probability is just half. Like, yeah, I'm saying that basically, yeah, there is some worst case scenario where there is no k clique. Yeah, we're not doing stuff case by case. Um, yeah, we're considering all of them. If it's still unclear, it's okay. I can try to make this more clear because this is kind of hard, especially if it's the first time you're seeing these kind of arguments. When you read them again and again, they kind of become more intuitive. But the entire idea in all of our probabilistic arguments is always going to be do stuff randomly and then see what happened. And now, after everything has happened, now you choose what you wanted. And what your choice is going to be the thing that is below your expected value, because you know that that exists. There's always something that's below the average. That's the rule. Yeah, that's the basic idea. Uh, Other people also, is it clear or is something else hanging, or okay, get it, but like I'm not sure. I don't know. Is this from the IMO? No, this is a research paper. Uh, Very old, like uh, I think Edwards or someone wrote about this. I'm not sure. But yeah, this is like super well known. Like if you go and study Ramsey numbers and extremal graph theory, they like assume you know all sorts of probabilistic and they just say this. Like, come on, these kind of things should be trivial to research people writers, right? But yeah, it's quite cool. Um, yeah. Do people want an even harder question, or was this too much and now we want a little bit relaxed question? Like, okay, maybe a better question is, do people want to see me doing lots of algebra, or yeah, we have 8 minutes. That's not too great, but we can extend because Pranav said you can extend this mission. So
Don't extend more than 20 minutes probably.
okay, cool. But yeah, I mean that'll be enough, right? So rule number one right now is don't get scared. Yeah. So we have something. We also have some stuff. I don't know what all of this means. Yeah, I'll manage. Don't worry, brother. You can go at it. Um, yeah, okay. You can always change your decision, right? If you think this is too bad, we can always go to slightly nicer looking question. In fact, I like this question more because it's just nicer. But that one is probably more, what do you say, uh, instructive because it teaches you a new idea. Which one? First or second? First one, you're saying. I'm assuming previous ones first. Let's do first one, but just post the second one after class. Yes, sure. The second one is, that being said, not easy by any standards. It's quite tricky, but it does not use any idea I have not discussed till now. This one uses an idea we have not really seen much till now. And that idea is that we don't do stuff with 50% probability. We do stuff with P probability and we pick P at the end. So what you'll notice here is because we did stuff with 50%, we got all of this half here. If we had not done half, we would have got P. And at the end, we would have got some sort of expression in P. And now if we maximize that expression using calculus, like it's a one variable thing. So you can find the minima by taking derivatives, if that's clear to people. If not, basically there is some way to, yeah, I'll explain dominating side. Don't wait for it a bit. I'm just explaining the idea of this question a bit. Um, yeah, no, probability matters the most. Like here, you can say kind of probability didn't really matter. We got lucky that even saying just 50% worked out. But now you have to be, now what will happen is this only works out if you pick P to be equal to 0.816. Otherwise, your inequality is too weak. But if you, not 0.816, like that, I just put a random number, but there is some value of P at which this inequality works out, and at others it doesn't work out. So you have to choose this value at the end based on the inequality rather than starting with the value of P and hoping that the inequality is true. So it doesn't affect the construction. No, construction, um, uh, I'm not so sure of what exactly you mean by this. Yes, I'm explaining that. So, okay, basically you have a graph. Graph basically okay, maybe I should just be more, I'll just delete this for now. I'll put it back at the end if people want to try. Graph is a set of vertices and edges. Come on, people, I've taken 3 classes. By now you should have learned graph theory. Okay, graph is a set of vertices and edges. And basically vertices are like points, edges are like lines joining them, but it's not geometry. So this thing is the same as this thing. Like whether I do it like this or this, it does not matter. Basically, what matters is that person one and person four are connected. Whether they were connected like this or like this is irrelevant. It's not geometry. And we define the dominating set. So what this basically means is you have, let's say, 1, 2, 3, 4, 5, 6, 7 people. Some sets of them are friends or joined by an edge. Something happens. And now you are saying, first of all, the minimum degree is delta more than 1. Why more than 1? I'm not sure actually. Does it not work for delta equal 1? It works because it just says n. But that's just sad if you need to do that. No, it doesn't work. You get n by 2 and everything could be 0. Okay, maybe it doesn't work. Never mind. Um, yeah, so dominating set is basically like you take a subset of the people, let's say one, two, three, four. No, does that work? Yeah, that works. And now actually not just these, but basically anything that's in your set or that's adjacent to something in your set is counted. So this guy is also counted because it's adjacent to this guy and this guy. This guy is adjacent to this guy. This guy is adjacent to this guy. So basically everything gets counted one way or the other. Either it's directly a part of the set or it's connected to some, it's like directly connected to something that's um, in the set. Also, I'll give an example of what isn't. This isn't because here, if you draw the stuff, it'll be like this is there, this is there, this is there, but this is not there and this is not there because there's nothing. This like none of the red ones are adjacent to this person. So this is not a part of your total thing. And this also, both of them are yellow, but they're not red. You need one of the neighbors at least to be red. So dominating set is basically the set of smallest size, these red people, so that when you take the yellow and red thing together, it should cover everyone. So for example, over there, I guess answer is four and maybe not. Let's see, what's the best way to do stuff? Um, Probably ideal to take this person and this. Yeah, okay. You can just do three people because now this guy is covered, this guy is covered, this is covered, and this is covered. Oops, what's misaligning? But yeah, okay. Everything gets covered. And yeah, the point is you want a dominating set, but it should be very of a small size, as small as possible. Because if you make everything red, that's also a dominating set, obviously, because everything is there in red union yellow. But that's not what we want. We want it to have this much size, which is like approximately n by delta into log delta. But okay, n log delta by delta, something like that. Let's say delta is like 20. So the minimum degree in your graph, which means each person is connected to at least 20 people or delta people in general. So here the minimum degree is two. No, it's one only. Sorry, because this guy's only connected to one person. But for instance, if I connected these two, now degree is delta is two. No problem. I'll explain again. So you choose a subset of the people and color them red, right? And you color everyone who is a neighbor of a red person yellow. So you colored these three people red, and then you colored this person yellow because it's a neighbor of this guy, this person yellow because it's a neighbor of this guy, this because this, and this because this. And now you want that red union yellow should cover everybody. But there should be as less red people as possible. So essentially, in some sense, you're like, what is the minimum number of people I should go to so that if they go and tell their immediate friends as well, I've told everyone the information in some sense. For example, what would not be a dominating set would be something like just this red, right? Because now, no, shit, even that is dominating. I'll have to add more stuff. Yeah. So now just this red is not dominating because this guy has no red neighbor. Is it clear now? Yeah, cool. Clear to the other people? Yeah, and we need to prove this. Yellow guys don't tell others. Yeah, yeah. If yellow guys also tell others, then eventually everyone tells everybody. That'll something like that will happen. So in fact, if your graph was connected, so there was a way to get from anyone to anyone, then that would mean dominating set is size one because this guy tells this guy tells this guy, and so on. But yeah, like then the answer would actually just be number of connected components. Here connected components are two because this is a connected and these four is a connected. But that's not the question. Only immediate friends. like neighbors. And yeah, we need to prove this ridiculous expression. And I gave you people a starting point, right? Because we don't know where to begin, we pick each guy to be red with probability P. So we've picked each guy, and some people have got picked. In fact, n into p people have got picked. Where p is like, I don't know, half, then half the people would have got picked. If p was 1 by 1,000, then n by 1,000 people would have got picked, etc. And now, if something has become yellow, great job. But if something is not, yeah, that's the expected value. But we're not done just yet because not everything is yellow. We need to add more stuff. So the point is, if something has become yellow, great. But if something is not yellow even now, that means that all of its neighbors were not red, right? Like if you picked red people to be like random people, but something did not become yellow, that basically means that all of its neighbors were not chosen to be red, which happens with probability 1 minus p. And it has, let's say, d neighbors. So the probability that none of them are red is 1 minus p raised to d. Uh, oh, right, is this right? Yeah. Okay. Yeah. So wait 1 second. I'm a bit confused now. And also we know that we need to be a bit careful. Basically, what I'm trying to say is that this guy is not going to get chosen, and none of its friends are also have not got chosen. That happens with very less probability. But when that happens, we just add it to our set. Like there were originally NP people at an average expected value, but by linearity, we can add in more people so that every guy who is not yellow, we make that guy also red, and then we take the expected value. I think we have to find P for any K vertices being a down and minimize K and maximize P. Yeah, we don't really bother about K just yet. Basically, we will show that expected value of that thing is near K by maximizing or minimize. Sorry, minimize. If no, you like set P so that the expression is minimized. And when the expression is minimized, that means that there's a dominating set of a very small size because the expected value of that size set is small. So yeah, you're minimizing K by doing something with P. You don't know what. Yeah, I'm slightly worried about the details here. I remember we have to do some E raised to stuff. So actually, I don't really remember the exact inequality. Maybe let me just find it. Because this was a tricky thing, like a very smart idea that they did, algebraic. So I don't remember algebra stuff. Yes. So what they have said is, oh, okay. What I did only. Yes. So, okay, not just D, but also D plus 1, because the yellow guy himself was also not picked as red. So 1 minus P raised to D plus 1. And this is true for each person. So we get the expected value as NP plus N times this ridiculous thing. N into P plus 1 minus O. Yeah, we can't multiply by N just yet because the D is different for each person. Yeah. That's the part where stuff gets tricky. So now you have to do something that's algebra stuff, which is say that 1 minus P raised to D plus 1. What's the sign? Let me just see. Okay, it's e raised to p into d plus 1 minus, I think. Yeah, e raised to minus p d plus 1. Wow. Uh, okay. Oh, also, we know that the minimum degree is d. So we can say that we can actually just replace this with delta because we're doing sine stuff. Like, I don't want to figure out whether d was bigger or not, is it? Uh, yeah, 1 minus p is less than 1. So it all works out nicely. Okay, cool. Yeah, why does this work out? That's a good question to ask. Um, Basically, you can show that 1 minus, uh, yeah, we want to show 1 minus p is less equal to e raised to minus p. This should be true. Um, yeah, okay. Yeah, the simple way of showing this is that e raised to uh, what's the best way to show this? I think what you need to do is define e raised to x as something equal plus 1 by n raised to n. Huh. Okay, this is left as an exercise to the reader. Like this is probably doable. This is mostly going to be some sort of algebraic trick. You're probably going to use definition of E, which is limit n tending to infinity, 1 plus 1 by n raised to n. Okay. I got it. Yeah. Limit n tending to infinity, 1 plus 1 by n raised to n. And this is E. So e raised to minus p will become this thing. And this, by Bernoulli's theorem, is more than 1 minus p because it's 1 plus 1 by n into minus p, minus np. Yeah, yeah, I think that just works. Yeah, you'll have to do for negative this thing expansion for binomial, so you need to know this sort of stuff. This is a research lemma, is it? Good question. Let's see. This is actually from Pranav Sriram. It just calls the problem dominating set. So yeah, it's probably a research thing. Otherwise, he would have mentioned which olympiad it's from. So yeah, it's probably uh, like, oh no, this result is probably like supposed to be trivial, which we were struggling on. But the entire result of this final thing is probably a research paper. Yeah. Okay, we have somehow got here. So we need n into p plus e raised to minus p times delta plus 1. This is the expected value of our set size. And if you notice, n is over here also. So we can like kind of cancel stuff off. And we basically want to show that this thing is we can make this equal to 1 plus log of delta plus 1 by delta plus 1. And now this is just standard calculus because I'm going to take derivative. I'm going to find the place where p is the p dash is f dash is 0. I'm going to set that as p. I'll do the stuff. You get this value. Don't ask me to do that. But if you want some help, I can tell you that the value of p you get is equal to any elementary proof? Not at all. I'm pretty sure no, because this is coming and you need to do calculus. Uh, like there is a simpler problem, which is like a slightly weaker version of this, which doesn't write log stuff. It's that's completely elementary. In fact, even that's there in the graph theory chapter in Pranav Sriram's book. But in the probabilistic chapter, he has shown this much um, uh, more accurate or whatever, stronger claim. And yeah, so this if by choosing p equal this value, see that I can show you because that's quite easy because the derivative of this becomes like 1 plus e raised to minus p delta plus 1 times 1 by delta. Okay, I'm not doing it. I'm gonna mess something up and then I'll feel bad. Yeah, it's okay. It says delta plus 1, minus delta plus 1. Yeah, you get this is equal to 0. So this goes there, stuff goes, you take log, you get this. Yeah, this is just sad. And yeah, you put this back in. All the best for doing that, but I won't be there for you. Okay, actually, it's not bad at all. Yeah. This is works out because you put it in, you get log d plus 1 by d plus 1, and then this thing, log d plus 1 just comes out, and you get delta plus 1, the whole raised to 1 or something, or minus 1. Yeah, you get minus 1. So it becomes 1 by this, and you add it. Is that what we had to prove? I hope that's what we had to prove. Yes, that's what we have to prove. Okay, so it works out. See, come on, people, you made me do this stupid algebra. It's so sad. But yeah, this is a very cool idea to take probability as P and maximize stuff at the end. And yeah, this was a very hard problem and very hard to solve. Like honestly, I see this in a context. I see log and delta and all dominating set. I go, oh, next question. Um, but that's actually the no. I don't mind algebra. I don't like inequalities type stuff. Like I love functional equations and all. But yeah, I don't like. It seems simple if someone exactly like the fact that you have to pick stuff with probability p. Okay, then you have to think of stuff that never got picked. Okay, then you have to add stuff. Then you have to minimize that expression. Oh my god, we are never thinking of that. But honestly, if you've seen this, if this comes again later on, it's kind of more motivated. Like the first time you see it, it'll be like, what the hell? But second time, it seems, this person has used this standard sort of trick and he's made his own problem or her problem. Um, but yeah, this will take time to come across, even if you've seen it 1,000 times. And that happens. Like I spent a lot of time before Inmo and all teaching this trick in graph theory, like standard thing. If you have n edges and n vertices as a cyclic. But that becomes super useful in places where you don't even know you need to make a graph. And then the Inmo problem came in. Inmo P5, Pranjal's problem, the other Pranjal. And there also you didn't know you have to make a graph. And the entire idea is to create a cycle there. I didn't think of it. But I was like, after the exam, come on, I was telling everyone to keep thinking of that and I couldn't. But yeah, that was a very good problem. And so was all of these, I hope. And unfortunately, I don't think too many people joined today, but I'm not too disappointed because one, people who came were talking, and two, I expect a lot of people will watch recordings because honestly, if I was in your place, that's what I would do. Um, I'm in class 12, just moved to 12th. Uh, it just came to 12th. I was in 11th. Um, yeah. Nice problem set. Instead of that, I can suggest that you read Pranav Sriram's chapter on it. It's very hard, but not much harder than what you saw today. Please post easier problems, other ones. Yes, sure. I'll just post them on OMC. I have a fair few problems that I couldn't do because time, but no problem. Yeah. Also, Pranav Sriram is hard, and everyone says that. And honestly, one of the okay, maybe I should no. Let's continue recording. It's not really hard actually. Honestly, if you read the solutions, it kind of makes you fall in love with what you're learning. But if you read the solutions, that also means that you lose the chance to solve such a good problem. Yeah, I mean, yeah, I agree. Like, it's better to do stuff on your own because when I did Pranav Sriram, that meant that a lot of nice problems I got solved. Guys, point. But it comes with its advantages. Like, I love comedy today. Um, hmm. And I think it's a fair investment of time because, uh, yeah, favorite topic combi by far. I don't have anything against the other ones. Also, I love geometry. I also love most of our functional equations. We'll not talk about inequalities. Second one I'll probably say is geometry. And then, oh, first FEs, then geometry. Okay, maybe I should stop recording.